Good afternoon, everyone. We have a special DSG seminar this afternoon. It's part of my grad course, but Tilmann agreed to make it a more broadly available. We're very happy to have Tilmann Rabl as our speaker. He's a professor at University of Potsdam and at Hasso-Plattner Institute. Tilmann is no stranger to Canada after finishing his PhD in 2011 at University of Passau. He spent 4 years at University of Toronto and then moved to Technical University of Berlin as a guest visiting professor. And since 2019, is at University of Potsdam and Hasso-Plattner Institute. His group has been doing great work on using GPUs, and I think one of the papers that he's going to talk about today won an award. So we're very much looking forward to his talk. Floor is yours, Tilmann.
Okay, so Tama, thank you very much for the introduction. So I can skip the intro slide on me, and I'm just going to take a few seconds to introduce Hasso-Plattner Institute because it's not really well known, I guess. It's a nice little institute at the vicinity of Berlin. So this is basically what I want to get across, right? So if you ever are in the area of Berlin, then visit us because this is our, like the institute. You can probably see my mouse. So this is our main building. This is where I would be sitting if I'm not at home. And while this is Potsdam, this is already Berlin, right? So this is basically really at the border of Berlin. And here we have a train station that is one stop away from Berlin and really nicely connected. And we're like a real computer science institute with bachelor's and master's programs and PhD programs. And we're also a department of the University of Potsdam, which is kind of unique because we're privately funded by initially or overall this guy. So this is Hasso-Plattner. He's one of the founders of SAP, which is also well known to you because they have like a big installation in Waterloo, and I know there's quite some collaboration with you. And but let's say we're quite glad that he basically put a lot of funding into his foundation or a lot of money into the foundation, which funds us and enables us to do a lot of research in databases, but all kinds of computer science research. Okay. So with that, let me almost get into it. So we're doing, like my group is doing database research, like all kinds of research. I don't want to go into too much detail, but one part is modern hardware. So say data processing on GPU. And we're usually doing some kind of application scenario, do a lot of benchmarking and benchmark development. And with this, also, like if we see there is something to do, we can get some speed ups or improvements and can extend systems with modern hardware. Then we do this, and we also try, like if we see, okay, there's like extending isn't enough, then we also build new systems. And the work that I'm going to present today is really work of my students, and all of them have already nice jobs in industry by now. So this is like the GPU join that I will show to you is done by Clemens Lutz. He's now at NVIDIA, and the sorting was done by Tobias Maltenberger and Ivan Illich. And Tobias is now at Google, and Ivan at InstaDeep, or Deep, I think it's a deep startup on AI, of course. And so what I want to present to you today is a quick one-on-one on data processing on GPU. So basically just give you a quick motivation on data processing or why we need hardware, and then how we can use GPUs to do that, or some rough overview of data processing on GPU and how GPUs work in the first place. Then we'll go to the scalable joins. So how can we implement a join on a GPU, and especially on a modern GPU? So this is really the focus. And then we'll go into, and there I have a typo, multi-GPU sorting. So what if we have multiple GPU in a single system? How can we use them for data processing? And of course, the reason why we want to do this is we have more and more data. Everybody's interested, and I basically don't need to tell you this, right? So if we want, we have more and more data, and we need to process it fast. Because the value is decreasing with its age. People don't want to wait forever. And so we want to really use the hardware as efficiently as possible. And why do we want to use the hardware, or why do we have to care about hardware? And this is because the hardware challenge. So in the past, essentially until the mid 2000s, we had like scalability of software or program just became faster just by waiting for the next CPU. So you can see up until around here, like 2004, the number of transistors per CPU were just doubling, also per core basically were doubling, and we would see like an exponential increase in single thread performance. And up until here, this was working fine, but then all of a sudden, the power limit was hit. So we couldn't get more power into a single CPU core. And because of that, vendors started adding more cores to CPUs. So from then, what we have now is like quad cores, whatever, like more and more cores in your CPUs. And there, we're also getting to a limit these days. And this is why we need additional specialization. So initially, we had single threads. Then we had multiple threads. So from here on, we need to think about parallel programming, because otherwise our software wouldn't scale anymore. And since we're getting to a point where just adding more cores doesn't really make any sense anymore, or is not beneficial anymore, because we're just like the sizes of CPUs are getting too large. Now we need more specialization. And having more specialization means we have more specific kind of processors. And this also means we really need to be hardware aware in order to make use of this. And this is not something that I'm just coming up with, but this is also something we see in industry, right? So if we look at Google, for example, they will say, well, we really need these tightly integrated scale-up special hardware in order to stay efficient. Then this is really the only way in how they can keep or meet their growing compute demands. So in the past, it would basically just be, okay, let's build another data center, and they scaled up their compute infrastructure by a factor of 10,000, I think, the last 10 years or so, or the last 20 years, and this is not going to work, right? So they cannot grow, like build a factor of 10,000 more data centers easily without just plastering the whole world with data centers. So it really needs more specialization in the hardware. And this also means, of course, in order to make this use as efficient, we need to be hardware conscious and make the systems efficient as well. And one way of doing so is really using specialized hardware like GPUs. And as I said, so in any point of time, feel free to, at any point, like ask questions in between and interrupt me if something's unclear, right? So one type of hardware where we have specialized computation is GPUs. So, and there was already a raised hand, so feel free to speak up.
It's just from your first few slides, just you were, so what I understand that, is it hardware which is guiding the software customization, or is it the opposite? It's kind of chicken and egg problem, I guess.
So yes, it's a chicken and egg. So in one way, here we really see, well, from this point in time where we have like multiple cores, it's really hardware that says, okay, we need to rewrite software, right? So in order to still get this kind of scalability from this point on, programs need to be written in a different way. Also, as soon as we need more performance, yes, again, we need to change the hardware specifically. However, of course, the type of computation that we need to do also guides the type of hardware that we see. So if we think about this TPU cloud, for example, this is specifically built for machine learning applications, right? All of these kind of tensor processing that we need to do in order to do machine learning. So in this case, the application also guides the hardware. So it's this kind of like a circular thing. But what we see for sure is kind of this trend to more tight integration, to more specialization, in contrast to what we've seen, let's say, 20 years, 15 years ago, where we say, okay, let's use generic hardware and just scale out, have more and more hardware of the same type. So right now the trend is quite the opposite, where we say, well, let's have this more scale-up hardware with much more specialization, because this is going to be much more efficient than just using more hardware. Does this answer your question? Okay, great. Okay, so and one type of processor that we see and that I'll talk about today is a GPU, right? And so a GPU, you all know it, you probably all have it in your system, is a highly specialized code processing chip. So it's usually used as an accelerator, and traditionally or initially was built for image rendering. So really just to show images faster on your screen, for games, for everything, right? And while CPUs have kind of increased in performance by 1.8 per year, GPUs have been growing even much faster, and they're more specialized, so they don't need to do any kind of computation. They mostly, or initially, were built for these simple parallel computations that you have in image rendering. And it's very parallel because we basically see like every kind of pixel would be an independent or would be a parallel computation. And over the time, people saw, okay, this we can also use for processing, right? For general purpose processing. This we call, some people will call general purpose GPUs or GPGPUs. And so this is mainly if we have basic, simple parallel computations, so multiplication, things like that, where we do the same kind of computations many times, then a GPU is a nice alternative to a CPU. So CPU is very generic. We can do all kinds of different operations. And we're trying to minimize latency between different tasks. So we have a very latency-oriented designs with tens of cores. So a modern CPU that you will get will probably not have, in a server, will have tens of cores. Very few have over 100 cores. GPU cores have much, or GPUs have many more cores than CPUs, but they have a lot less infrastructure for decoding and encoding instructions. So they basically, a lot of cores will do the same processing in parallel and on different units, but the same kind of computation in a sort of a lockstep or interleaved manner. So you cannot like have individual cores run completely different tasks, but you will have larger units of cores do the same kind of tasks in parallel. And here we're not talking about tens of cores, but we're talking about thousands of cores. And we're really trying to get a high throughput, not so much a very high, very low latency, but a high throughput. So here also we will have much higher throughput in terms of memory bandwidth than we will see. And so you can see that the CPU typically has hundreds of gigabytes of memory bandwidth, while the GPU can have thousands of gigabytes of memory bandwidth these days. So here are the numbers for the A100 and H100, which would, like, H100 is the top-notch GPU that you will get from NVIDIA. And most of my slides right now are based on NVIDIA stuff, but the same thing holds true for also AMD chips. So the modern AMD GPUs will be in the same range in terms of number of cores, throughput, or high bandwidth memory throughput. And it's important, it's a separate processor. You have many cores that do the same thing. And you basically need like some certain computation to get them running. So they need to have multiple things to do, or this, like, you need this kind of data parallelism where you have the same task on multiple data items or multiple things that you compute in order to make efficient use of them. If you do many different tasks, like you would do in a multi-threaded environment on the CPU, the GPU won't help you much. Okay, so from a memory hierarchy perspective, the GPU usually is always connected with some kind of interconnect to the host memory. So we have the DRAM that's next to the CPU, which can be terabytes. Then we have the global GPU memory, so which is which is on the GPU accelerator, and here we have some kind of interconnect, which could be PCI Express or NVLink. I'm going to show you some other also interconnects. I'm going to go into more detail in a few slides. And then we have the global memory, and then much smaller L2 cache, which is shared across all compute units. And then we have very small local caches and local memories, which then the compute units or shared multiprocessors have, where then we have multiple cores within that really need to do the same kind of processing within. So we have a compute unit that has many cores, and that will need to do the same task in parallel. But we can actually have multiple different tasks across multiple compute units on the GPU these days. In the beginning, there was just like, we would just have a single one. And the throughput increases the further we go up. And so the global memory, we can also already have like terabytes of memory bandwidth, which is much higher than the bandwidth that we would get on DRAM, for example, on the CPU. Okay, so with this, so as a rough overview of the GPU is usually connected to the CPU in one way or the other. Let's go to the interconnects, because this is traditionally the real problem why the GPU would not be beneficial for data processing, right? So if we want to do data processing, so have a database basically utilize, or a database management system utilize the GPU in one way or the other, we need to get the data into the GPU. And this is through the GPU interconnect. And the traditional interconnect that GPUs would be connected to in most servers these days, and especially in the past, would be PCI Express, right? So this is one of the general interconnects in your servers, where you can have SSDs like storage, you can have all network connected, or accelerators like GPUs, FPGAs, and things like that. And for a long time, most systems had PCI Express 3.0, which gives you something like 16 gigabytes per second, right? And there we're at the speed which is much lower than the throughput that the CPU can get, right? CPU has hundreds of gigabytes per second. And now we're at 16 gigabytes per second that we can get through the PCI Express. So this would be like such a typical PCI Express connection. If you ever opened up like a server, then you will have seen these connectors. So this is basically data connections. This is power. And we will have, like, for each individual slot, we will have, or for each individual lane, we will have like these multiple connectors, like back and forth and positive and negative, in order to have like a correct transmission. And here we can see like this is a single connector, 4 connectors, 8, etc. And this would be like your typical GPU connection. This is still increasing, so there's been a lot of speed because GPUs need more interconnect and more bandwidth. There's been a lot of development going on. So even though, like, say 4 years ago or 5 years ago, PCI Express 3.0 was the thing, and you would rarely get anything above that. So PCI 4.0, I don't exactly know when these systems started, but I think 4 years ago we had the first system with PCI Express 4.0. So where we would get 32 gigabytes per second. But now we also have 5.0 already, and there we also have like a new abstraction, which is the Compute Express link, which gives you even more, like also gives you cache coherent access across this interconnect. But I'm not going to go into more details here. So this is one way, and the traditional way we would be connected. And here we can see this is really a limitation, right? So if we have fast interconnect or fast memory and high bandwidth on the GPU, if we need to move data back and forth, this will be a problem. A different interconnect is NVLink. So this is NVIDIA specific, but there's like similar things on other hardware. And initially, this was mainly just to bridge different kind of GPUs. Right, so this would be like actually the physical device to connect to NVIDIA GPU accelerator cards, or the physical entity that you would plug on top in order to have a faster interconnect in between two GPUs and then communicate and basically exchange data that they have in memory. So you can use multiple GPUs at the same time. And with NVLink 2.0, we already would have up to 250 gigabytes per second. 3.0, 300 gigabytes per second, and now we're at 4.0, which has 900 gigabytes per second. So there we're all of a sudden in the range or even above the range of what like a CPU memory bandwidth we can get. As I said, initially only in between GPUs, but now we can also have this all the way to the CPU, which then gives us a throughput and a bandwidth that we can use in order to really read the data fast enough to make it work, or to also keep the GPU busy and make it faster than the CPU would be. Okay, so with this, I'm going to show you a few examples of like deployments or systems, what they would look like some examples, then some bandwidth numbers, so what we can actually get if we have these kind of systems in terms of throughput, and then we'll go into the actual algorithm. Okay, so this would be your traditional setup with PCI Express. So this, if you buy a regular GPU server, this is what it will probably look like. You have one CPU or two CPUs, you have some like larger memory, and then you have PCI Express and two GPUs connected there, which then will be interconnected with NVLink. And if we have PCI Express 4.0, so this is something that we have, for example, in our lab, we have one AMD Threadripper, then two NVIDIA GPUs, so equivalent to the V100 roundabout. And these are connected with NVLink 3.0 in here, but with this 32 gigabytes per second to the CPU. So we can see the GPUs are connected faster with each other, but have this PCI Express connection. And the memory, I didn't put this here, but here we'll have something like 150 gigabyte per second roundabout that the CPU can get. So we'll definitely be bottlenecked by this connection here, right? Then like something like what is a unicorn and that we've been using a lot in our experiments, but which was kind of like a first system in a row, was the AC922 by IBM. So this is a power machine which has NVIDIA GPUs where we can have NVLink to the main memory or to the CPU. Right, so instead of using PCI Express, this GPU is connected with NVLink to the CPU memory, this GPU, and is also connected to the other GPU. So here we have a symmetric connection in between the GPUs and the CPU, and with this, the GPU can read the data as fast from the CPU as it can read it from another GPU. And it can read it much faster than in traditional setups, right? So before we saw here, we have 32 gigabytes. Here we are at 75 gigabytes. The CPU has 170 gigabytes to the main memory. So reading with both, we're getting in the area of the CPU speed when accessing the memory. Across different systems, so this is also interesting here, this is the cross-bus for IBM. So this is how fast like NUMA nodes are basically connected. We can see that this is actually slower than the connection to the GPU. So going across here will be slower than going like reading from this CPU. This memory will be slower than the GPU reading from this memory. And as I said, this is a unicorn. So this was the only system built like this. Nowadays, we have other systems that actually also have this kind of setup, or NVIDIA built something by themselves that has a similar setup. I also have a slide on this. The current system that you can get is, looks something like this. So this is the previous generation, so DGX A100. Now we have the H100, where we have 8 GPUs, 2 CPUs, we have large amounts of memory, and then the GPUs are connected with PCI Express to the CPU, but they are interconnected with NV switch. So they have like a complete interconnection, like a network basically, where each GPU can communicate with each other with very high throughput. And in the A100, we have the NVLink 3.0, so with 300 gigabytes per second. In the H100, which would be the next generation, where we have the H100 GPUs, there we would have 900 gigabytes per second. But still, if we're at PCI Express 4.0, we're still at 32 gigabytes per second to the CPU. So definitely we'll have the bottleneck here again, but we'll have very fast interconnect and very fast exchange across the GPUs. And so finally, what we're really excited about, and there's like our first development system that we have, and we've not really had the chance to do any experiments. So this is very new, is the Grace Hopper architecture by NVIDIA. And again, there's a similar system coming up by AMD, where we have the CPU and the GPU directly connected with NVLink. So this is the Grace CPU, an ARM-based system directly built by NVIDIA. And there we have NVLink, again, directly to the CPU. So we have NVLink with 900 gigabytes per second. And this is basically in contrast to the earlier 16 gigabytes per second, right? So we're almost 2 orders of magnitude faster than the old system, and we're much faster than the initial like memory bandwidth. So here we can really speed up processing in the GPU, and we're mostly going to be bottlenecked by the memory rather than by the GPU interconnect. Okay, so with this as an overview, as an interconnect, so this is basically what we're dealing with, right? When we're doing algorithms and doing processing, it's always, we have to think about where does the memory reside? Where do we keep the memory? And then what are what will be our bottleneck? And in the very old, or not very old setup, recent setup, still PCI Express 3.0 is not that old, right? In this setup, we would always be bottlenecked by this interconnect. So in this case, and this is also why a lot of people thought using the GPU for data processing doesn't really make much sense, because this is where we're always stuck. But as soon as we have NVLink with 900 gigabytes per second here, then it actually makes sense to use the GPU and use this high bandwidth. And here you can see on the GPU, we can get like, as soon as we have the data in the GPU memory, we have even 3 terabytes per second of bandwidth. So then we can get even higher bandwidth than what we could do on a CPU. So then we always have to think, okay, what is basically our bottleneck? Do we have more computation? Do we have more memory accesses? Then it makes basically sense to think like, where do we place computation? Where do we place the data? And all of a sudden, also hybrid setups make sense. And this is basically what we'll use in our GPU join in a bit. But before that, let's look at a few numbers in terms of data transfers. It's not super surprising. If we think about this PCI Express 4.0 setup that I showed you, if we have the data, like we're always looking at the data being in main memory. So if we're reading from main memory, we're sending the data to the GPU or to the memory, so both directions, we're going to have like a same kind of setup. So we're getting 26 gigabytes per second which roughly makes sense with the theoretical 32 gigabytes with all the like protocol overhead that we would see. If we're doing this in parallel back and forth at the same time, then we'll roughly double this, so we can even get a bit faster. And we can even do this in parallel across multiple systems. So then we're even faster. So we can utilize these connections in parallel across. And we can also copy in between the GPU nodes. So here we can see we can copy from 0 to 1. We can copy from 1 to 0. So this is again symmetric, but we can also do in parallel back and forth. So there's parallel connections to those, and we get even higher throughput, right? So this is faster. So this connection again is faster in between the GPUs than the CPU, the GPU to CPU connection. If we look at this AC922, so this power machine where we have NVLink to the CPU, there we can see the numbers are much higher, right? So here we were at 26 gigabyte per second, and here we're at 72, which is close to the 75 that we will see. And again, like going both directions, we're not completely doubling it, so we're at 170 to 122. If we have to go across the cross bus, then we can see this is limited by the cross bus, right? So this is basically if we read from 2 or 3 from this, so our data is always located at memory CPU 0. Then if we go through here, we will always be limited by the 64 gigabyte per second in the cross bus. Yes, and there's a question.
Yes. Hey, can you hear me?
Yes, I can.
So I think this paints sort of it doesn't paint the whole picture, right? Because what are the scenarios where you actually want to go to the CPU? Like, what are the workloads where you have to go to the CPU all the time? Let's say you can fit all the weights. Like, let's say you're training a model, a machine learning model, and you can fit all the weights in the GPU memory.
Right.
Then is there any reason to go to CPU at all?
So if it's a good question. So what if everything fits onto the GPU? Then yes, you can stay in the GPU for as long as you can, right? So you can do all the processing. We're talking about data processing. So the assumption is that we have to deal with data sets that in many cases are larger than the GPU memory. And so if the assumption is everything fits into GPU memory, then we only will be bottlenecked once. So if we read the data and for processing, eventually in a database system, we want to have our data somewhere in some kind of durable storage. So for just computing stuff, it's fine, but we want to have the data in the main memory eventually, and also on disk. So there will always be at some point we will need to do the transfer. If we think about doing many operations on the GPU, one after the other, then we could stay in the GPU. Eventually, the results will need to go back to the CPU again in order to be like output. Does this make sense?
Yeah. So the data that you're showing right now, these data transfers, these are basically assuming that you're going to the CPU all the time? Like,
yes. So this is there's no computation here at all so far. This is really just data transfers here. So at this stage, we're just looking at how fast can we move data back and forth from the GPU. Okay.
Thanks.
Okay. So the idea here is just to basically give you I just want to give you an overview of what are the data transfer rates that we can see. So given these different kind of setups, and here important is really that we have a very nice throughput between the GPU and the CPU memory, so we can really read fastly from the CPU memory to the GPU and back. So this is what we need in data processing if we need to materialize the results in main memory to give it back to the user. There's different ways also to transfer data out of the GPU through the network directly, but in the end, we need the results out of the GPU again, and we need to get the data into the GPU. And the assumption is in this work and in many database works as well, that the data sets won't all fit into the GPU all the time. So then we need to transfer back and forth. And what we also see that we have nice like in between GPU throughput, but if we need to go across the cross bus, right, this will be also our limitation. And then finally, just as an overview, I need to speed up here a bit, is for the NV switch architecture. And here you can already imagine, like in between the GPUs, we get very nice throughput. And overall, if we can like connect all GPUs to all, we can get up to 2 terabytes of throughput through this NV switch architecture, which is much more than what we can get through the CPUs, because the CPUs will basically always will be limited by the PCI Express. And we always have 2 GPUs connected to 1 PCI Express lane, so they will basically share. There's also a bit of there's a bit of difference in between throughput across different kind of GPUs. So the closely connected GPUs have higher throughput than the more far connected GPUs. So there's more information in the papers that I'm going to share later. But overall, the NV switch gives us better throughput than the PCI Express. And if we would have to go through this UPI connection in this case, or Infinity Fabric, this is in AMD, so it would be Infinity Fabric, then this would be for sure the limiting factor rather than going through NV switch here. So looking at this so far, it's important that we know that we basically have to be topology aware. So this is very important, right? So looking at this AC922, for example, it makes sense to utilize like one CPU with the GPUs connected, because there we have very high bandwidth. As soon as we go across the cross bus here, this will be a limiting factor. And utilizing this, we can actually now go into the scalable GPU joins, right? So now we're going to do some real processing. So far, we've just been shuffling data around across the different kind of systems. And now I want to quickly show you the pump up the volume, or our scalable GPU join, which utilizes a single GPU, but exactly this kind of hardware, right? So where we have NVLink. And this is also the kind of hardware that we see that is kind of coming in new generations. So new generations of GPU have this really high interconnect. So we're using the super fast interconnect in between the CPU and the GPU to get scalable and actually efficient processing across CPU and GPU, right? So the idea is that we scale GPU data management to arbitrary data volumes. So in general, if we have a GPU, and we want to do also machine learning, right? So the common assumption is everything needs to fit onto the GPU memory. If we're going out of GPU memory, then we basically have a problem, right? So in our database will be terabytes of data in many cases, and our GPU memory will be gigabytes. So the V100s that we're using in these experiments, for example, have 16 gigabytes of memory. This is not a lot for a database workload. Larger GPUs might have 80 gigabytes. This might be good for many cases, but large databases go in the terabytes or even petabytes. So you cannot load all of the data in there. So you need to somehow be efficient in your transfers. So, and the problem really is this transfer bandwidth, right? So you have your database typically in the main memory, and you want to do the data processing in the GPU. And so somehow you need to deal with this ad hoc transfers, right? And if we have PCI 3.0, this will be 13 or 12 gigabytes per second back and forth, which is a lot less than what the GPU can actually process in terms of bandwidth. It's also a lot less than what the CPU will be able to process, because database workloads are usually not as compute intensive as general like machine learning workloads would be, right? Where you have a bit of data and then do a lot of iterations on it. And in GPU and database workloads, there are like much more filtering, comparisons, etc., as you would have in a join. So the GPU is capable of much higher throughput than what this PCI Express can give you. So, and this is called the transfer bottleneck. And this was for a long time a problem, but now we have these higher throughputs, which we have, for example, through this NVLink architecture or in the Grace Hopper architecture, where we actually have 900 gigabytes per second rather than the 75 gigabytes per second, right? So this means we're getting to a throughput that is as fast as the memory throughput that we can have on the CPU. And so in this case, for example, so if we look at this architecture, then we can see that from a theoretical point of view, we get 5x improvement over this PCI Express, and we're actually at memory speed in terms of throughput when accessing or transferring data from and to the GPU in parallel, right? So a single GPU will not be as fast as the memory, but usually utilizing multiple GPUs, we can actually get to a transfer speed that is on par with the main memory speed here. So if we want to do data processing as an example, we do a hash join, right? So our hash join will be the example, and there's different ways in scaling this. So a general hash join, I guess all of you are aware of how a hash join works, right? So we have a build phase and we have a probe phase. So the build phase basically means we're building a hash table out of one of the two relations. And then in the probe phase, we're going to probe the hash table with the second relations to find out where we have joint partners. And the probe side scaling is basically the simpler one. So as soon as we have, or we can build a hash table in the GPU, and then basically have we're just creating a hash table that fits into the GPU, and then using the high bandwidth or the fast interconnect to just stream the data into the GPU while we're doing the hashing in parallel. Like, as we know, the GPU is highly parallel, in parallel doing the lookups in the hash table on the GPU. And if we do this, then for the probe size scaling, we can see we can go even beyond GPU memory with the probe relation size, which of course makes sense, right? So we have in this case, we're joining a 2 gigabyte table with an up to 122 gigabyte table. And then I'm comparing here a traditional CPU-based join, so hash join, then PCI Express hash-based hash join, and we're not partitioning here. So we're just basically having a single hash table, and we're probing with a much or up to much larger second table that into the hash table. So, and here we can see that this is basically what fits into the GPU memory. Our hash table is in the GPU memory, and then the NVLink based version is basically scaling even after we're going beyond the GPU memory, because we're just utilizing the fast throughput. So we have radix in this case, we have a radix partitioned hash join on the CPU baseline, and then we have a PCI Express based version that just reads the data through the PCI Express, and it's limited by the PCI Express bandwidth. And we have our NVLink version that utilizes just this high interconnect, just reading on, like, transferring the data on demand to the GPU and doing the probing on the GPU. So we get a 6 times improvement over the CPU baseline in this case. And we show that GPUs can efficiently process large out-of-core data on the GPU, but just for the probing so far, right? So this is the easy case. Now, the question is, what happens if we actually want to scale the build side? So this is the more complex part, right? So the build side means we're building, so the probing means we're just sequentially reading the second relation, basically block by block, transferring it to the GPU and doing the hash lookups in parallel and sending the results back. So this is a very sequential and very high throughput approach, or very sequential problem. Now, if we want to do build side scaling, this means our hash table all of a sudden grows out of the GPU memory, and we might have like random independent lookups or random independent writes into the CPU memory. So this means we're basically doing the hashing on the GPU. So we're loading the initial relation or the build relation into the GPU, computing the hash keys, and then building the hash table that is in the main memory, in the CPU memory. And there we can actually do data-dependent memory access. So we can utilize basically the way that the memory is exposed to the GPU in a cache coherent manner to the GPU, and basically still be efficient by when building the hash table, right? So and here you can basically see the same kind of results, or not the same results. So here we're building, or we're doing the same kind of join, but in this case, increasing the build relation, so increasing the relation that we built the hash table with beyond the memory, the GPU memory size. So in this case, we have the same kind of baseline. So we have the radix join on the CPU in order to be parallel on the CPU and just not using the GPU at all. We have the PCI Express based version, and we have the NVLink version. And when everything fits into the GPU memory, so the hash table itself fits into the GPU memory, we get the same throughput that we saw earlier, very nice and flat. And the same also for the PCI Express. But as soon as we're getting larger than GPU memory, then all of a sudden we're basically completely bound by the individual latency of the NVLink or the PCI Express, right? And so this means all of a sudden our NVLink based version will go down if we don't do anything smart. It will go down to basically the same kind of throughput that we would see on the CPU baseline. And our PCI Express based version will actually go down to a throughput that is much worse than what we would see with the CPU baseline. So we're actually much slower here. And so the drop in performance is basically 85% if we go out of memory, right? And we have like PCI Express is even like not a factor of 6 slower, but a factor of 18 slower in this case. So now what we can actually do, rather than just using like a main memory based hash table in this case, we can have a hybrid hash table. So we can use a hash table that uses the virtualized or virtual memory where we first allocate memory in GPU. So we have a larger virtual address space. We're first allocating memory in GPU, but as soon as we're spilling over or we need too much memory, then we're going to go to the main CPU main memory. So some of the accesses will go to the main memory, but as long as we're in GPU memory, we will be local. And if we have this kind of hybrid hash table, then we can see the data actually, or the join actually more gracefully degrades in size. We're still going to get slower. Eventually, we're completely limited by this NVLink latency because most of the accesses will go to the CPU memory, like individual hash accesses. But for some time, we're actually staying at a much higher throughput than we would have with the CPU baseline, and much higher throughput than we would have with the basic GPU baseline, where we have every access will basically go to the CPU main memory. So, and with this, we can actually also operate on large out-of-core data structures, but we need to cache data as much as possible on the GPU memory. And so in this case, like this is basically the gist, what we did in the pump up the volume. So we basically saw that using the NVLink, like this fast interconnects, we can actually scale the GPU. In many cases, we'll get very good performance for the build side, probe side scaling. We saw that we can like really outperform the CPU by a lot. And but we can also go like for the build phase out of core, so we can still be faster than the CPU baseline for a certain data size. But we need this fine-grained cooperative co-processing. And the hardware accelerators and the fast interconnects are really the key trick here. And this is not like, this is basically just checking how fast can we be with these throughputs. So, but there's kind of a sneak peek here that we did a follow-up on this, which is the Triton join. And there we use partitioning also for the GPU based join. So our initial join was no partitioning. So we have one large hash table everything goes into. And this means as soon as the hash table grows out of the GPU memory, all of a sudden we're not going to be as fast anymore because we have these random accesses to the CPU memory. If we're partitioning, we can be sure that our accesses stay in GPU memory, and then we can actually scale out of the GPU memory, right? So this is our Triton join. So if we're doing the partitioning will have a bit of an overhead if we stay in the GPU memory. So in this case, like the no partitioning join, which we showed earlier, is actually faster. But as soon as we're going out of GPU memory, with the partitioning, we're still much faster. We still have this very high throughput, which is significantly faster than the CPU, and also significantly faster than what the no partitioning join would be able to do. So with this, I'm basically almost through on time, I see. So I have like, I would give you a sneak peek still on the multi-GPU processing, but I'll check with Tamer first, like how we're doing here, or if there are questions up to here.
Yes, if there are questions, we can take them. Otherwise, you can go for some more, maybe another 10 minutes or so, and then
Okay, so there is a question. Feel free to.
There are two questions.
Yes.
Okay.
So Ida.
Yeah, Ida, will you go first?
Yes. Hello. So I have actually two questions. The first one is about the data. So you, in the first part of your talk, you discussed the data flow and architecture. I am wondering what happens to the data when the processor is done with that data, like for example, in case of streaming data, when the processor is done with one batch of data, what happens to that data? Where do the data go to, and and what happens to the garbage? And my second question is about the last part that we were talking about, and the hash tables. Here, by the hash table, you mean the table that includes the actual data, or the routing data is also included in the topics that you were mentioning, especially
Yeah. So I didn't fully catch the second question. So the first question is like, what happens to data that is on the GPU, right? So let me maybe answer this first and then maybe repeat the second question because I didn't fully understand it. So the first question is essentially in this case, we're like, if we you can see the GPU memory as a cache. So we'll buffer data that's been sent to the GPU. If we can reuse it, we will reuse it. But if not, it would just get overwritten. So if we're doing like, say we're doing this partitioning and like as in this hierarchical partitioning and the radix partition GPU hash join will load the data into the GPU if just like in a hybrid hash join. If we can use the data, we'll use it for the join. If we need the memory space for something else, we'll overwrite it. So the data will just be lost. The data set itself will stay in main memory. So that's the assumption. And the second question, I didn't fully understand.
My question is, what could you explain what is one entry of the hash table that you are discussing in your
Yes.
diagram?
So the question is basically what goes into this hash table and what we're building and probing, right? And these are the join keys. So in this case, we're trying to compare. So if we're joining two relations, we'll usually have like a join key that that we need to compare. And in a hash join, we're hashing this join key. So we build a hash out of the join key, and then we're comparing these hashes. So with this, we have like a very simple way of comparing the joins, or we just build a hash table where we have like where we store like hash values, or based on the hash value, we restore the join keys in the right buckets. So, but in GPU joins, we'll typically really work with hashes of the keys. So we're hashing the key, and then we're comparing the hash values. And if two hash values match, then we have a join partner. We might still have to materialize the join afterwards. So first we just need, okay, we just know which keys are matching, and then we need to later on also materialize the complete record later on. So we just join the keys, and then we know which keys are joining, and then we materialize the complete final result. Does this answer your question?
Thank you.
Okay, so there was another question by Arman.
Yeah, Arman.
So my question is that considering that when we use GPUs for the databases operations like this, we only get like 6 or 7 times speed up compared to CPU optimized algorithms. And considering that GPUs actually cost much more than CPUs and they actually use more power, can't we just throw in more CPU cores to compute our problem rather than using GPUs, especially considering that programming GPUs is actually harder and more tricky, and using heterogeneous computations actually makes it much more harder?
That's a very good question. So looking at this, right? So this is basically the architecture that we're using in this case is on the one hand, the CPU and the GPU, the prices are not that different. So while the GPU is expensive, these server like upscale CPUs are actually also quite expensive. So in the end, the price difference is not like that much. So if we get like in this case, if we get a 6 times speed up, the GPU is not 6 times more expensive than the CPU here. So that's one. And the other thing is that while we can use more CPUs, the interconnect in between the CPUs is actually slower than the interconnect between the GPU and the CPU here, right? So with this, we can actually be faster than what we can be across multiple CPUs, because the CPUs all in all won't get the same kind of bandwidth here. So in the end, because the GPU is really this like high bandwidth architecture, if we want this very high bandwidth and very high throughput kind of workload, then utilizing the GPU will actually be faster overall. So we won't get this kind of throughput with just CPUs. if considering we have one data set, as soon as we can completely split this up across many CPUs and be super parallel, then yes, we can get like even larger throughput. But here in this tightly integrated setup, there's not a way to get like a same kind of throughput with this kind of CPU. Does this make sense?
Yes, thank you.
You're welcome.
There's one more question.
In a minute, yeah.
Yes,
Yeah.
I think it's a very simple question, but so all the things you are joining as a data processing in the GPU is the joining, right? The radix joining, as you mentioned. So that means all the data models are your either key value or relational data, like model. But do you have any suggestions, like if the data is graph and we want to process that in GPU, which is mostly like running BFS or DFS, that might change the scenario a little bit?
So for now, we've only looked at the joins, or let's say equi-joins and sorting, and looking at graph. So I would assume you need is like a similar kind of mindset in how you process the data here. So you like a BFS would probably work well. Depth first search, I would have to think about how you can nicely parallelize this in the same kind of way, right? So it's if you can translate it to a sorting and parallel processing architecture, yes, should be doable. And we're looking at other kind of operations as well. But for now, this is basically just to have like a starting point. We went for GPU joins and sorting to reflect what kind of processing is possible here.
Tilmann, I think even in graphs you could utilize joins, because you could actually think about edge tables and joins, of both BFS and DFS becoming joins, self-joins over edge tables. So partitioning edge tables might you'll get to the join at the physical level.
So I mean, if you translate the graph problem into a relational table or into a table kind of tabular kind of problem, then very easy you can apply the same kind of techniques. Yes. It really depends on the type. Like if you have a very iterative algorithm, it's might be, well, it's probably still you can translate it and you can still make it work. And we did some work on like iterative algorithms as well. But I'm not really deep, to be honest, I'm not really deep in graph processing to tell you like what are the typical kind of workloads and do they nicely translate to GPU problems. Yeah, so that's why I'm a bit cautious, to be honest.
Yeah.
Okay.
Come on, there's one more question from
Yes.
Amin.
Hello. So I wanted to ask, it's kind of similar to the other question. And my question is, how do you think one would build a generalized system? So would it be like building specialized operators, like supporting other things than equi-joins? I'm making aware of these specialized computing platforms, or do you think it's also possible to build something generalized that works for all of these operators?
So let me ask you back, what do you mean by system? Do you mean like a database system?
Yeah.
Or,
the database system, yeah.
Database system. So current approaches look at this from a library point of view. So meaning that you build individual operators that then you can utilize in libraries, as you would do in like machine learning libraries, basically saying you have the different kind of operators and then you plug them together, and they can be translated to the different kind of architectures, or they try to be generic for the different kind of architectures. So that's one way to go. I think honestly, I think this is also right now, it's the way to go, to basically say, okay, what are the dimensions of variability that you have across the different kind of hardware? And how can I translate this across, or how do I have to parameterize my operators based on that? And then I utilize it in the operations or in the library. If I want to build a system where this is like, yeah, we've been thinking about it. I mean, there you get the kind of the next dimension is really the data size, right? As soon as, like, if everything fits in the GPU memory or in multiple GPU memory, all of a sudden we can do things much faster or much different than if we actually need to, like, in every step of the computation, need to go back to the main memory. So they're basically looking at the, like what I said earlier, you really have to be topology aware and data size aware, let's say.
I see. Thank you. Thank you.
You're welcome.
Tilmann, there's one more question.
Yes.
Sairaj, go ahead.
Hi. I heard you mention, so I saw you mention NVLink and NVSwitch. I was just wondering, have you guys looked at GPU Direct RDMA, just how that compares here? I've read a little bit about it, but I'm not sure if it is applicable
Honestly,
here.
yes. So we haven't. There's a paper by Carsten Binnick's group on GPUs, GPU joins using the RDMA and across multiple GPUs. So TU Darmstadt, they did something there. We haven't tried it, to be honest. So I know it exists. It should also be scalable. The difference is here using NVLink, you have cache coherence. So you don't really, like, you can really use like a large virtual address space and let the GPU and the CPU negotiate where data is located, and then get really nice throughput through the interconnect. And I think this is also where things are heading with the Compute Express link. So this is also where we will see cache coherence across accelerator memory and CPU memory. So I think this is the kind of what at least the next generation of systems will have. So with RDMA, you really have to do this yourself, right? So you really, you can also get very nice throughput, but you have to, like, be a bit more, much more low level in terms of communication. So, but there is work that you can look into, or that's, I can also share the link to that.
Awesome. Thank you.
You're welcome.
Tilmann, we're coming to the end, about
Yes,
five
that's perfectly
minutes.
fine.
Do you think there's a way to summarize what you wanted to say in about 5 minutes, or?
Yes, for sure.
Okay.
I will. So I
Okay,
mean,
I'll leave
yes.
it to you then. Yeah.
Okay, perfect. So I think this one you kind of get, okay, we can scale out of like single GPU memory, and we can be efficient. And I think this is very important, right? So we can be efficient in the sense that with utilizing the GPU, we are faster than using the CPU. And we might even be cost efficient in terms of, like, looking at server grade upscale CPUs and GPUs. And if we have the GPU anyway, then it totally makes sense to use it. So we're not wasting anything. We're not wasting CPU cycles, etc. So now what we also looked at is what if we have multiple GPUs, right? So this was always only one single GPU. Now we can also have multiple GPUs, and we use this for sorting initially. We also have work going on joins right now. And so there's different kind of algorithms. Because of time reasons, I'm not going to go into much detail. I'm just going to show you the takeaways here. So it's like we're using the same kind of architecture again. So we're using this AC922, which has 4 GPUs, 2 CPUs, and 2 GPUs are always connected to a single GPU. And we have this DGX A100, where we have 8 GPUs, which are using NVLink or NVSwitch, all connected. And then the CPUs And the assumption is the data will be located in memory somewhere. So it's located in memory somewhere, and we need the output in the end in memory somewhere. If if we're doing this on the DGX, on the AC922, then on a single GPU, we can see that's like moving the data to the GPU and from the GPU costs us roughly about the same amount of time than sorting the data on the GPU. So this is basically what you can see here. So this will be faster than sorting on the CPU. So we can actually go faster than just using the CPU. If we use 2 GPUs, this like even scales up. So in this case, we basically have like sending the data to the GPU, which is less than like basically halving the amount of time than just sending it to a single GPU, because we have twice the bandwidth. Then we have to exchange in between. So we're sorting locally, which is kind of this here. We have to exchange in between these GPUs, and we have to send back. And we need to do this, or in order to be efficient, we need to interleave the data transfer and the actual computation, as you can see here. And doing this on GPU, actually with 2 GPUs, we're going to be, well, not half the time, but almost half the time. So we're actually scaling nicely. If we're using 4 GPUs, it's going to be slower. And this is really because of this bottleneck in between the 2 CPUs, right? So this is basically all, we're slower than using a single GPU. So this doesn't really make sense, right? So the architecture that we saw earlier with the AC922, where we have NVLink, this is actually really good for doing this kind of work. And this is even the fastest compared to doing this on the A100, right? The A100, this is a V100 GPU. The A100 is like has many more cores, is like much higher performance, has much higher throughput. But in the end, because we are here bound by the PCI Express interconnect, we're never going to be as fast as on this one, right? So we're basically even going for 8 GPUs. We see that here this scales up to 8 GPUs because we have multiple PCI Express connections. But we're never as fast because in the end, we're always bound by this data transfers, right? So this is always what kind of limits us. But with these Grace Hopper architectures, we're actually like, we'll repeat these experiments, and we'll probably see that here we can get even faster throughputs overall, and like much higher, I mean, an order of magnitude higher, lower end-to-end duration, just because we have an order of magnitude higher throughput in the end. And then also utilizing multiple GPUs for this will again make sense. So we'll see some scalability with these faster interconnects, right? Again, so we need like topology awareness in order to be fast in utilizing GPUs. Having fast interconnects will give us performance benefits, and not only like total performance benefits, but also efficient, right? So we're going to be faster than a CPU, and we can even be like price performance wise efficient, but only if we have fast interconnects. Otherwise, this like it scales, but it's not really efficient, right? So using 8 GPUs for the sorting, we're still not faster than these 2 GPUs here. And so this is like, there's different kind of strategies. This is all explained in our papers, how we can do this. And right now we're working on a join algorithm that goes across these multiple GPUs. And hopefully we'll have some experiments on this new Grace Hopper architectures. So wrapping up, what I wanted to show you is GPU accelerated data processing, and that it actually makes sense to do this, right? So we can utilize the GPU efficiently if we have fast interconnects. I think that's the essential part. And if we're utilizing them smartly and we're working GPU or like interconnect and topology aware. And so I showed you like the joins, how joins scale, like just briefly mentioned sorting, and we'll soon come up or show, we have already some results on multi-GPU joins And then we'll also try to like basically have full database workloads on the GPU. So complete queries, which then again makes sense, right? Because all of a sudden, like the more computation we can, the more we can stay on the GPU and are not bound by the interconnect, the more the higher the benefits in the end. So thank you very much. Thanks a lot for the question. I hope this was useful for you. If you have further questions, feel free to reach out. And I've also sent the slides, so you can look at the other details that I've skipped. Yes, thanks.
Thank you very much, Tilmann. Much appreciated. It was very useful, and we took a lot of your time, but it was very much appreciated.